Hey everyone, I got a request to make a video for a DFA example. So in this video, I'm going to take you through constructing a DFA for the given language here. The language of all binary strings that have an even number of zeros or an odd number of ones. So if you remember the example we saw in class, from the description of the language, we kind of jumped right in. But in general, this isn't necessarily the best strategy. So I'm going to show you something else that we could do first before starting to draw the states. Now, the key thing to remember about DFAs is that they process strings from left to right. So at any point in the computation, they've seen some part of a string, but they also have some part left to go. And because they always go from left to right, once you've read in some characters over here, you can't access those letters again. So instead, states have to remember something about the part of the string that's been seen so far. The real question when designing DFAs is, what do they actually need to remember about the string? Do they need to remember every character that's been seen so far? Usually not. Usually it's enough that the states just remember some property about the string that's been seen so far. And we formalize these properties using state invariance. Often you can try to figure this out by looking at the complementary property. At a given state, what are we expecting to see? Or what are we waiting for in order to accept? So one thing that you can do if you're having trouble getting started writing a DFA is just write down some strings which should be in the language or should not be in the language. Consider the string 0, 0, which has an even number of zeros and therefore is an L. So because 0, 0 is an L, we know that if the DFA reads in 0, 0, it should end up at an accepting state. But if the string isn't complete yet, the next letter might be a 0 or it might be a 1. And these lead to two different outcomes. If I consider the string 0, 0, 0, well now this string has an odd number of zeros, but an even number of ones because 0 is even. So that means this string is not an L. On the other hand, the string 0, 0, 1, so this string is an L. Depending on how complicated the language is, maybe these two string examples aren't enough to really get a good feeling for what the language is supposed to be like. So you might try thinking about the string 1, 1, which is actually not in the language, and then thinking about what happens when you read in a 0 or when you read in a 1. But this sort of experimentation is usually too limited to find patterns. So let me remind you that what we're really trying to do is not just figure out where 0, 0 reaches, but really whatever state 0, 0 reaches, what property that state is trying to remember. And to get hints about this, often you can look at the language description. So in this case, an even number of zeros or an odd number of ones. So what if I thought the property that really is important about 0, 0 at this point is that 0, 0 has an even number of zeros? Well, certainly if I had the string 0, 0, 0, 0, and then I read in either a 0 or a 1, then I'd get the same result happening of either being an L or not being an L. So maybe this means I should have a state in my DFA which is just even number of zeros. And all the strings that have an even number of zeros reach this state. And I could even try to fill in some transitions. So for example, over here on a 0, I reach a state that I know should not be accepting because of this. And on a 1, I should reach a state that is accepting because of this. But there are at least two problems with what I've drawn so far, and they're both quite important. So the first is, remember that these properties, so whatever I write kind of here, eventually I want to translate that into a state invariant. And all of the different invariants should be mutually exclusive. And that's really not going to work out with this example of invariant here, an even number of zeros. If I start with a string that has an even number of zeros in it, and then I read in a 1 to get to this state, to get to this accepting state, well, this new string, it still has an even number of zeros. that tells me that not every string that has an even number of zeros reaches this state. And this is a hint that whatever I've written here isn't really specific enough. But there's another problem too. So what if I took this string 001 and I said, oh, it's an even number of zeros, therefore it should reach this state. And then what happens if after reaching this state, I read in a 0? Well, then I transition here, so I know that 0010 should end up in this state, which means it should be in the language, but it reaches a rejecting state. So this is a bad state invariant. It had the right idea, but it wasn't specific enough. Maybe our state invariants or our properties should have something to do with, we're going to have 4 states. And rather than give them labels like I normally, I'll just write down their invariants inside the circles. Now before moving forward with drawing my DFA, I'd just like to point out that these cases are actually very natural when you're looking at the original question. So one thing I could have tried to do along these lines is just take a look at the original language description and then write down 4 strings, one for each representative case. That is maybe something like 0, 0 for an even number of zeros, even number of ones, 0, 0, 1, 0, and 0, 1. Oh, and by the way, here's a hint for when you're studying for the final. These 4 strings, which I got from talking about the different cases that strings could satisfy related to these properties. These 4 strings, they're all distinguishable from each other. If you manage to figure out these 4 strings are distinguishable first before drawing the DFA, this gives you a hint that you'll need at least 4 states in your DFA, which is what I've drawn over here. So first of all, let me try drawing in some transitions. And you might notice that with these state invariants, it's actually quite easy to draw transitions, because I know that, for example, if I have an even number of zeros and an even number of ones, if I read in a 0, then I'm going to end up with an odd number of zeros and an even number of ones. And similarly, if I'm at that state and I read in a 0, then I go back to an even number of zeros. So I'll just skip ahead to having drawn in all the transitions. At this point, our DFA is looking pretty good, but we're missing 2 things. We're missing where the initial state is and which ones the final states are. It's not necessarily obvious which one of these we should start at until we remember that, the empty string should always satisfy the invariant of the initial state. And in this case, the empty string has 0 zeros and 0 ones, and since 0 is an even number, it has an even number of zeros and an even number of ones. That means that this should be the initial state. What about the accepting states? Well, to this, I go back to my language description. I'm looking for the states where either there's an even number of zeros or an odd number of ones. And it's not too hard to see that, well, these 2 have even zeros, and these 2 have an odd number of ones. So in fact, these 3 states are all accepting, and this is the only rejecting state. So that's the process I went through to draw this DFA. Notice that my process didn't immediately start by drawing some pictures. It instead played around with some strings to try to figure out what was important about these strings, and really trying to get a good understanding of the actual English description of the language and how this might influence my state invariants. As I said in class, coming up with state invariants isn't something that you should do at the very end after you've drawn the DFA. It's really something that you should be doing as you're coming up with the DFA. Just as when you write some code, you don't try to figure out what the loop does after you've written it. You figure out what the loop should be doing as you're writing it. And finally, here's a bonus tip for you. While DFAs are pretty bad at counting forever because they only have a finite amount of memory, DFAs are really good at counting with remainder. So this question here was really about calculating the remainders of some numbers when you divide by 2. But you can imagine, instead of saying that W has an even number of zeros, I could have said W has, say, a number of zeros, say minus 5 is divisible by 7. When you divide the number of zeros by 7, you get 5 as the remainder. I'll leave it as an exercise for you to figure out how to draw a DFA accepting this language. But to make sure you're on the right track, I'll just tell you that such a DFA would have something like 14 states. And that's all for this video. Thanks for watching and have a great day.